Hello, everybody. So in sections 6.2 and 6.3, we are going to use integration to find volumes of certain types of solids, right? Section 2, we do these well-known methods called the disk method and the washer method. And in section 6.3, we will learn another method called the shell method, all right? And so those are very different, but they do accomplish the same thing, which is to find the volumes of solids of revolution. So let's take a look at it. Section 6.2. All right, volumes by slicing. What do I mean by slicing? I think it will make perfect sense once I explain what that means, right? So I have very casually hand-drawn graph here from A to B. Let's say the function is something like this. This time I tried to make it a little simpler. And so the idea here for the next two sections is to revolve this function about an axis, all right? So you know this axis is known as the x-axis, right? So what happens if you take this region, okay, and then just let this go around the x-axis. So imagine you have a three-dimensional space like this, right? And right now you just have this. And then if you rotate this about this axis here, what's going to happen is, of course, it's going to make this circle here and then circle here. And you will have what is known as a solid of revolution, or a solid obtained by rotation or revolution about the x-axis. All right. So if you rotate this, okay, about or around or on the x-axis, you will get something that looks sort of like this. Okay, and you better learn how to draw 3 dimensions or things in 3-dimensional space, because as you study calculus, you will see more and more applications of things in 3 dimensions. The good news is you don't have to draw in 4 or 5 or higher dimensions, even though you may still do mathematics in these higher dimensional spaces, right? And now the job is, or now our task is, to find the volume of such solids. Okay, again, these are called solids of revolution, not the kind where you oust your government. Okay, that's also revolution, but here it just means revolve, rotate, to turn in the circular motion, right? So, by the way, what can you do when you do something like this? The idea is easy to understand if you first understand the whole idea of integration. Remember what an integration was? Of course you do, because we just talked about this at the beginning of chapter 6. In 6.1, at the beginning of 6.1, I said what? The method of integration, or the idea of integration, is basically accumulation. It's a continuous as opposed to discrete. It's a continuous version of addition, right? So you have the simple addition, like 1 plus 2 plus 5 plus whatever. You can always add a finite number of finite numbers, but what happens if you have infinitely many of them? And that's when you have to take the limit of Riemann sums, and that is the idea of integration. So you still have points from A to B, okay? And for each x between A and B, you're going to assign a number, okay? And that number used to be called f of x. And then you integrate f of x from A to B, and that would be the accumulated sum of all of those points, or the line segments between 0 and whatever the f of x was. But this time, it's not that you are integrating f of x, because as you imagine this, and this is where the slicing comes in. Imagine slicing this into a bunch of pieces, okay? So each part is going to be looking like a thin disk. All right, let's pick one of them, and let's see what it looks like. All right, so pick this point x, and right around x is this very thin slice, okay? If you try to find the integration or the volume by slicing, which is what we're trying to say to do in section 6.2, if you slice this thing, each slice is going to look like this. Okay, now this length is, of course, what we used to call delta x, or if this is not evenly distributed, if it's not evenly sliced, i.e. if it's not regular partition, then you each of these slices will have its own thickness, or the length of the subinterval, which we denoted as delta of xi, right? And then the height, or the radius of this disk is actually f of x. If you can just imagine this, remember we started with a function f of x, right? So each disk is of this form. The radius is f of x, okay? And the thickness is, as before, delta xi, right? And so what am I going to be adding along x? What is the value assigned for each x between A and B? It's almost like you're squeezed, see, you have this disk here. The entire disk, the volume of this can be squeezed in right to the middle and give the weight for this, point x. If you do that, what kind of number should be are we accumulating? Are we going to be integrating? Well, that's obviously the area or the volume of this small disk, a slice. Okay, so the idea is to find the volume of this slice and add them up. Right? So the radius is f of x. The thickness is delta. Thickness, of course, is the height of the slice. Think of this as a circular cylinder, a very thin cylinder, and then the height of the cylinder is what we call delta xi, right? And so how big is this cylinder, or how big, what's the volume of this each slice? Well, the answer is, this is bi, maybe, the ith volume, right? The volume for the ith slice is going to be, well, it's pi r square, but r, the radius is that, so you square that, and that's going to give you the surface area of the circle. And then if you multiply this by the height of the cylinder, this will give you the volume of the cylinder. All right, so you add them up, and you have n of these. So that is what you get, okay? And then, of course, you just keep slicing them more and more, so you have many more slices. As n goes to infinity, you get your volume. And that volume, of course, is pi f squared and then dx, right? So here is a simple yet very powerful volume formula. So the volume by slicing, and this is called the disk method. Okay, now there are variations of this, so I will be talking about them in a minute, but the volume is simply the integral from A to B of pi. Now let's take the pi outside because that's a constant, right? So pi goes outside, and then you have fx squared dx. That's a very simple thing. So all you have to do under the disk method, and I hope you understand why and where this formula came from. Okay, all you have to do for the disk method is to integrate not f, but f squared as the radius squared times pi, which is going to give you the area of the circular part of the slice, and then you just integrate, from A to B, because for each point between A and B, now what you are trying to do is to integrate, to assign for each point the area of that circle, of the slice, which is pi times r squared, where r happens to be, as you can see in the picture, fx, right? So that's called the disk method. No problem here, right? Let's do an example of this. Maybe I should highlight this because it's an important, very important application of integral. It's one of those things, again, that you'll find in every calculus book, disk method. All right, so let's say you have, this is going to be cool. Okay. It looks hard, but it's not. So this is the square root of x. Y is equal to the square root of x. And let's say you integrate, or you're trying to find the volume of the solid of rotation or revolution obtained by this function y is equal to the square root of x from 0 to 4. All right, so you take this, and of course you revolve this or rotate this about the x-axis, and you're going to get something that looks like an acorn or a bullet, and you know, that's what you get. All right, what's the volume of this shell, or what's the volume of this big acorn? It's the integral from, it's pi times the integral from 0 to 4 of the function squared dx. Well, this function squared is even nicer than the function itself. It's just x dx. And so this is x squared over 2. There's a pi in front, of course. Okay, so this is 16 over 2 times pi. That's 8 pi. And so the volume of this shell, which is the solid of, solid obtained by revolving the function, the square root of x from 0 to 4, turns out to be 8 pi. All right, so this is not bad, right? Not bad at all. I think you'll find this relatively easy. All right, now let's go to, well, one of my favorite example. Okay, this time I'm going to do a straight line. Okay, so what's this line? Y is equal to, well, I'll tell you what, okay, the motivation for this next example is I want to come up with something that we already learned the formulas for, a formula for. Okay, so the volume of a, what is that? It's a circular cone, right? A circular cone, do you remember the volume of this? You may have learned this like in your middle school, depending on what kind of middle school you went to. Maybe you learned this in kindergarten, depending on which kindergarten you went to. But somewhere in your life, I think you learned that the volume of the cone is 1/3 times pi r squared h, okay? Where this is h and this is the radius r, okay? So the volume should be 1/3 pi r squared h, okay? So I think I learned this as a 7th grader in Japan. And, I'm just thinking, okay, this is cool, but where did the 1/3 come from? And, you could say, well, Archimedes in ancient Greece discovered it's 1/3 of the volume of the respective corresponding circular cylinder. And it is right, okay? If you take the circular cylinder and if you make a cone out of that, the volume of cone is exactly 1/3 of the volume of the cylinder. And it is true that Archimedes knew that 2,500 years ago, but that doesn't help, right? I mean, where did this 1/3 come from? And so if you are a keen middle school student, you should have asked that question, and not just because your teacher told you so, okay? You should always, try to pursue your curiosity and keep asking questions like, where did the 1/3 come from? Well, the 1/3 came from calculus. And of course, you didn't know that, and you could not have understood it back then as a 7th grader. But now is the time to understand it. Let's try to figure this out. All right, to create this cone of radius r and height h, of course, you want this to be 0 and h here, right? The x coordinate should be h here. And you want this to be r. So what's the function then? Okay, revolve the function y is equal to something. It's a linear function with a y-intercept of 0. Well, the slope is kind of easy to figure out. The slope is the rise over run, so it's r over h. All right, so that's the function that you have to revolve about the x-axis to get the cone, right? So it turns out the volume is going to be pi times the integral from 0 to h. Remember, h is this, fixed height. And then what's the function? It's going to be r over h, both of these are constant, times x. And then, of course, you square that function according to the disk method formula. And then that's it, all right? You just integrate this. And of course, r squared over h squared, that's a constant. The only thing you really have to integrate here is x squared, okay? And when you do that, you get 1/3 times x to the third. and you evaluate this from, well, you evaluate this at 0 and h. Let's just use that part here. Okay, so this is pi h squared on the bottom, r squared on the top, and then you have 3, and then you have h cubed on the top, and minus 0, right? So basically, I'm not going to write h cubed minus 0, which is, of course, h cubed. And so then things cancel, like h to the third just becomes h because you have 2 h's on the top. So this is what you get. And of course, that is equal to 1/3 pi r square h. And that is the formula you learned somewhere in your earlier life, right? And so this is the justification, or this is a way to justify that formula. Archimedes clearly did not use calculus, which did not exist until Newton and Leibniz in the 1600s. But somehow he figured this out using other methods, and now we know from calculus this is the correct formula. That 1/3 came from what? Integrating x squared, right? And that would clearly give you 3 as a part of your denominator, and that is the explanation for this. Again, you could not have understood this as a 7th grader unless you knew calculus back then, but this is how it is obtained. And so hopefully now you are satisfied. And sometimes, you know, you just have to take things just by faith, because you just don't understand. You don't have the intelligence to understand things. Your understanding is limited. All of our understanding is limited. And sometimes, you know, something could be true without you understanding what's happening or where certain things came from. But you know, there is that answer. And now we know, because we have a little more understanding of mathematics. All right, so that's the disk method. Let's go on to another. So in general, it does not have to be, the solid does not have to be obtained by revolution. In general, if you can slice a solid in some way where the slicing creates certain patterns, then you are still able to obtain the volume of such a solid. So in general, slicing works in similar ways. What happens if you don't have revolution or rotation? So if you, for instance, have, this is, you know, something that's hard to draw. Let's say if you have x here, y here, z here. This is how we typically draw a 3-dimensional space. Let's say you had a solid, which is something like this. And so what happens is it's like a triangular, it's sort of like a prism. Let's say you have this. And okay, so what do I have here? It is a solid called tetrahedron. Tetra means 4, hedron or hydra means face. It's a 4-sided solid. It's half of a pyramid, if you will. All right, and so let's say this point is 1, 1. Actually, it's 1, 1, 0 because the z coordinate is 0 here, right? And so basically, let's say this is height 1 and this is length 1 here, and you have this solid. Okay, you see what's going on here? And if I were to just give additional details, this, so the what you see here is a tetrahedron. And it's 1 by 1, okay, meaning that the base of this tetrahedron is this triangle, which happens to be a right and isosceles triangle. The length here, so this point is 1. This is actually 0, 1, 0, okay? And this point is 0, 1, and the z coordinate is 1, okay? So what you see here is the tetrahedron where the base triangle is a 1 by 1 isosceles right triangle, and so is this side. That's also a 1 by 1 right triangle, isosceles triangle, and so is the back side, which is this side here. That's also a 1 by 1 right isosceles triangle. Okay, so how do you find the volume of this thing here? Well, for each y, a slice can be defined like this, right? So if you take this y, for instance, okay, this y between 0 and 1, as you can see, pick this arbitrary y, and the slice, if you slice this object at this point here like this, the slice is going to look like that. You see that? And it's very thin. But if you have to define thickness, it's going to be delta yi as before. Okay. But what is the slice is going to look like this? It's a right triangle. Okay, and it's a right isosceles triangle. And do you know what the length is here and here for each y? Well, as you can see here, this line is y is equal to x. Okay, that's why you get this point 1, 1, and the origin 0, 0, right? I mean, what you have here, if you look at this from the top, it's going to look like this. You know, going from 0 to 1, going from 0, 0 to 1, 1. And so the base triangle I drew is exactly this. You have to change the orientation from here to see, you know, and quite understand what's happening here. And for each y, I am trying to, actually, that's not true, is it? Okay, I take it back. It's a little complicated, more complicated than this. All right, so what we have is this thing like this, right? And this is the x-axis, this is the y-axis. The pink base of this tetrahedron, which I drew, is actually this part here. You see that? Right? And that's because you know, it's going along the y-axis, not the x-axis. I mean, x-axis is not adjacent to this tetrahedron. So so what I'm drawing here is this. If you pick this y between 0 and 1, the this slice that I drew, the black slice I drew, is actually going to be right on top of that segment, right? And so what is the x value? X goes from 0. This is y is equal to x. Or in this case, you should write as x is equal to y. So x goes from 0 to y. And that means this length is here is also equal to y. And of course, the height and the length are the same, so it's also y, right? So the slice, the area of this slice, the right isosceles triangle is 1/2 y squared. Okay, so it's 1/2 times the base times the height, so it's 1/2 times y, and that is the area of each slice at y, at each y between 0 and 1, and that is what you are trying to integrate, right? So the volume is going to be from 0 to 1, as y goes from 0 to 1, of the area of each slice, which is 1/2 y squared, and that's what you integrate. All right, there's no pi here because, you know, you don't have anything circular, and we are not finding the area of any circle. The slice is not a circle. The slice is a right isosceles triangle. So this will be 1/2, 1/3 y cubed, 0 to 1, and of course this is 1/6 times 1 minus 0, which is 1/6, right? And so that volume of the tetrahedron happens to be 1/6, right? And this is actually a well-known phenomena. If you start with any kind of a cube or even just a rectangular box, and if you take a tetrahedron, which is somewhat like this, just you know, this part here, that's 1/3 of the half. See, this is half of the box, right, or the cube. If you take the back half, which is somewhat like this, okay, and if you take the tetrahedron, which is like that, it's actually it's like a cone out inside of the it's like a cone inscribed in a circular cylinder. The answer is 1/3 of the volume of the cylinder, right? So this tetrahedron is actually 1/3 of half of this box, which is of course 1/2 of the cube. So it turns out to be 1/6 of the cube. And that is the explanation for that as well. But see, you can do the slicing even if you don't have a solid, which is obtained by revolution. Okay, now next we will do a disk, or the type of disk with a hole in it. So if you have a disk with a hole, what do you call that? Well, we will see that in a moment.